Hi, this is Taronish Pithawala, Technical Lead for Geophysical Modeling at Geosoft. This episode is 4 of a 5-part series on inversion best practices. In this video, you'll see why we recommend including magnetization vector inversions in your interpretations of magnetic data. You'll also learn about the MVI component outputs with a synthetic example so that you can explore an additional solution space with a new perspective and arrive at the best possible interpretation utilizing all the tools at hand. Previous episodes in this series can be found online and cover basic inversion principles, optimizing large datasets, and using constraints. The utility of magnetic field data in many areas of geophysical exploration is well known, as is the application of 3D voxel inversion to aid in magnetic data interpretation. In most inversion methods, it is assumed that the magnetic response arises entirely from magnetic induction. In the last decade, studies have shown that remnant, self-demagnetization, and other anisotropic phenomena are far more prevalent than previously thought, and they affect crustal rocks as well as zones of mineralization. These effects can distort inversions that are based on the assumption that the source magnetization is parallel to the inducing field. The severity of the distortion is due to the non-unique nature of potential field inversion. Therefore, it is very easy for a potential field inversion to produce a model which agrees with the observed data, even when a fundamental assumption is wrong. Here is a real-world example of a magnetic region in Brazil with a simplified cartoon on top. In the real example, the axis of magnetic rock follows the dotted white line. It is no simple task to interpret the TMI image due to the relatively low inclination of the Earth's field, but we can expect the inversion result to help us interpret the subsurface location of the magnetic rock. Inverting the observed data with the assumption that the rock's magnetization is parallel to the inducing field yields a result like this, viewed in cross-section across the axis of known mineralization given by this white line. The positive anomaly is offset from the true location and is adjacent to a strong negative anomaly. But allowing the rock's magnetization to lie along any direction paints a very different picture. You'll see here that the inversion was able to recover the location and orientation of the magnetic rock better than the conventional model. It is important to note that in terms of inversion success, both results match the observed field data equally well. It is the task of the interpreter to determine the fit between the geophysical and geological models. Several geoscientists have made progress towards magnetic data inversions that include remnant magnetization and other effects. Geosoft's Voxel Earth Modeling Service furthers those efforts with a technique called Magnetization Vector Inversion, or MVI. This method solves for the fundamental magnetic rock property, the magnetization vector, without requiring prior knowledge of remnant or anisotropic effects. We'll begin with a brief overview of what the magnetization vector is. The magnetization of a rock is a vector quantity measured in SI units, amperes per meter. For a given volume, it is defined as the number density of magnetic moments, N over V, multiplied by the mean of the magnetic moment vectors mu. The key importance of this quantity is that it allows us to represent the magnetic properties of a rock without making assumptions about the source and direction of magnetization. The magnetic field B observed at some point R, resulting from a volume V with a magnetization M, is then given by this expression here, which shows directly that given an observed magnetic field B, the natural parameter for inversion is the magnetization vector M. MVI therefore returns the magnetization vector, both its direction and amplitude, for interpretation. Of important note is that solving for M requires no prior information about the strength or direction of any possible remnant magnetization. MVI returns the magnetization vector regardless of how the source is magnetized. Now that we understand what fundamental property MVI is returning, we can explain the various components that are reported by Voxel when the inversion completes. To do so, we will proceed step by step through a synthetic example. Although the buried prism model is far too simplistic to have exploration significance, it does make an excellent educational example. Thus, we will consider the inversion of simulated TMI over a buried prism with magnetization vector perpendicular to the Earth field. We first construct the prism and examine its components so that we know what to expect from a reasonable inversion result. In a cross-section of the vector representation of the prism, we see that magnetization is solely in the easterly direction. The amplitude of magnetization within the prism is also shown in pink, and outside of the prism in light blue. Inside the prism, the amplitude is 1 SI, whereas outside, the amplitude is 0. In Voxel's MVI, the vector amplitude is normalized by the Earth field strength, and so the dimensions are analogous to susceptibility units. We expect a successful magnetization vector inversion to recover this easterly magnetization in the vicinity of the buried body. Before looking at the scalar components of the magnetization vector, we'll discuss two coordinate systems. Here, we see the Cartesian or XYZ coordinate system. X is positive east, Y positive north, and Z is positive up. The XYZ system is independent of the Earth's inducing field direction. The second coordinate system is rotated to align with the Earth's inducing field direction. The rotated UVW system is aligned so that U is positive in the direction of the Earth's field. And V and W are orthogonal to U and to each other, maintaining a right-hand convention. The same magnetization vector may be represented in either the UVW or the XYZ coordinate system, but it is important to note that the components are not interchangeable. Turning back to our prism example, you'll recall that the magnetization is easterly and the Earth's inducing field is pointing straight down with an inclination of 90 degrees. In the Cartesian or XYZ coordinate system, the magnetization is given by a single component, the positive X component. Cross-sections through the same part of the model space show that only the X component has a non-zero value in the vicinity of the prism. In the rotated or UVW coordinate system, the positive U direction is aligned with the Earth's inducing field. The easterly magnetization in this example is therefore only given by the positive W component. Cross-sections through the same part of the model space show that only the W component has a non-zero value in the vicinity of the prism. The magnetization vector can also be represented by the two scalar quantities we've termed E_perp and E_proj. These are respectively the components of the magnetization vector that are perpendicular to and projected onto the Earth's magnetic field direction. The components are given by these simple equations. E_perp is the component of the vector that lies within the plane perpendicular to the Earth's magnetic field. Thus, it is given by the sum of the squares of the two perpendicular axis components, V and W. E_proj is the component of the vector that is parallel to the Earth's magnetic field, and since U is aligned in this direction, it directly gives the E_proj quantity. For our simple prism model, the E_perp and E_proj components are as follows. Within the prism, magnetization is easterly and thus completely perpendicular to the downward Earth field. Consequently, there is no projected component within the prism. Outside the prism, magnetization is zero everywhere. To recap, we've described our prism model using a vector representation of the magnetization, and also using the scalar components in the XYZ coordinate system, the UVW coordinate system, and also using the projected and perpendicular components. When we run the inversion, we expect to recover a model that is similar to what we've seen. The magnetization vectors should be easterly in the vicinity of the prism and near zero in the background. The XYZ and UVW components, as well as E_perp and E_proj, should also reflect the vector components we just saw. We forward calculate the total magnetic intensity using an earth field with a 90-degree inclination and a 24,000 nanotesla amplitude. We then use this grid as input into our inversion. We first invert the TMI response to the buried prism using unconstrained conventional susceptibility inversion. Recall that the fundamental assumption in using this inversion method is that the magnetization is in the direction of the inducing field. We see that the inversion is unable to easily recover the location of the buried prism. In addition, the smooth model norm has created a broad positive and negative anomaly. It should be noted that the result fits the observed data to within 5% of the standard deviation, but it is not a good representation of the true subsurface. To better define the extents of the anomaly, I apply iterative reweighting inversion focusing on a subsequent model. Using IRI to focus both ends of the susceptibility distribution, we can see that the anomaly is more refined. However, the model still does not recover the true location of the buried prism. In fact, if we didn't have any insight into the magnetization direction of the prism, it would be quite difficult to decipher anything useful from this result. For later comparison, note that this inversion also fit the observed data to within 5% of the standard deviation, but it is still not in agreement with the true prism location. We now invert the same TMI response using magnetization vector inversion. By examining the amplitude of the magnetization vector result, which has been normalized by the inducing field strength to yield an analogous MVI susceptibility, we see that the MVI produces a weak positive anomaly in approximately the correct location. Furthermore, the magnetization direction is pretty much easterly, as we would expect. However, the result is too smooth in both amplitude and direction. Following the same steps as before, I apply IRI focusing to the positive end of the property distribution, since magnetization amplitude is always positive. With an IRI focusing of positive 2, we can see that the MVI recovers the position of the buried prism quite well. The MVI susceptibility product is also more straightforward to interpret compared to the conventional susceptibility. The recovered magnetization is pointing mainly to the east in the vicinity of the prism. Changes in direction for small vectors are due to the smooth model norm. Therefore, it is recommended that interpretation of magnetization direction is limited to vectors of high amplitude. Constraints, analogous to those used in conventional susceptibility modeling, like parameter reference models, can be used to further refine the MVI result. The MVI result fit the observed data as well as the other models, but it is clear that this model is a better representation of the true distribution of magnetization. The amplitude and vector voxel output of the MVI result are the primary products for interpretation. The vector voxel displays both the direction and amplitude of the magnetization, whereas the scalar amplitude voxel comes in handy when comparing the model to conventional susceptibility results. We recommend that MVI models are always calculated whenever interpreting magnetic data in order to analyze the solution space when the constraint on magnetization direction is removed. The MVI result can also be displayed in other scalar component forms, in the same light as we've done earlier with the buried prism. Analyzing the resulting components is another way to see if the inversion yielded an outcome that is consistent with other information. These components can be thought of as secondary interpretive products. This slide shows the x, y, and z component voxels along with the recovered vectors and an outline of the true prism. For each component, pink is high valued for that scalar, yellow is 0, and blue is largely negative. As expected, the vectors within the volume of the prism have a high scalar projection in the x component, with only a small component in z due to the smooth model norm. A small negative z component can be seen where the vectors are pointing slightly downward. The small positive z component corresponds to the slightly upward pointing vectors. The y component is near zero pretty much everywhere. Again, it is important to note that the interpretation of the vector direction should focus on vectors with high amplitude. Taking another view, we can look at the u-v-w components. The vectors within the prism volume have a strong w component, as we would expect. The v component is near zero everywhere. And lastly, there is a weak u component, positive where the vectors are tilting down, parallel to the inducing field, and negative where the vectors tilt up, opposite to the inducing field. This indicates that within the region of high amplitude vectors, the inducing field component of magnetization is weak. It can be inferred then that the fundamental assumption in conventional susceptibility modeling is flawed, and therefore MVI is the better choice for this particular example. The perpendicular and projected components of the magnetization vector are shown here as another way of representing the magnetization vector. Within the prism, the magnetization is mainly perpendicular to the inducing field, as it was in the true model. We see that the E-perp component has a large positive value. Away from the prism, the magnitude and direction of the vectors change, and E-perp begins to fall off to zero. Where decreasing amplitude and the smooth model norm tilt the vectors, we see a small positive and negative values in the E-proj voxel. Again, these small values should not be considered significant to your interpretation, as they are controlled mainly by the smooth model norm and not a geological or geophysical phenomena. As in the study of the other scalar components, comparison of E-perp to E-proj in regions of high vector amplitude show that for this particular model, the fundamental assumption in conventional susceptibility modeling is flawed. Indeed, if we had observed the opposite, if E-proj was much larger than E-perp in all regions of high amplitude, it could be said that constraining the magnetization direction along the Earth's inducing field, as is done in susceptibility inversion, would be a valid choice. The usefulness of these scalar components is obvious when working with real-world data. In such prism examples, the vector voxel is easy to view, and much insight can be gained just by viewing the high-amplitude vectors. But for inversions of real geophysical surveys, the size of the survey, compounded by the complexity of the result, can make the vector voxel difficult to interpret. Therefore, these two secondary components, E-perp and E-proj, can be used to gain some insight on the orientation of magnetization. For example, domains with significant E-perp contributions indicate regions where the magnetization vector is not aligned with the inducing field. This can be due to effects such as remnant magnetization, self-demagnetization, or magnetic anisotropy. As another example, domains with significant negative E-proj contributions can indicate that the anomaly is reversely magnetized. Or, if E-perp contributions are small everywhere, then magnetization is primarily along the inducing field direction. These observations can offer some intuition on how to better interpret or further constrain your models. To recap, we forward calculated the total magnetic intensity of a 100-meter cubic prism with easterly magnetization buried 50 meters beneath the surface with an IGRF inclination of 90 degrees. We then inverted the total magnetic intensity using both conventional susceptibility and magnetization vector inversion. The conventional susceptibility inversion was unable to easily resolve the prism because the method fundamentally assumes that the magnetization is parallel to the inducing field, which in this particular case is not true. The magnetization vector inversion makes no such assumption and was better able to recover the location and magnetization of the buried prism. The MVI result gave us information about the depth extent, magnetization direction, and amplitude of the buried prism reasonably well without any geological constraint. As a first attempt with minimal effort, the result is quite good and agrees with what we expected from analyzing the components of the forward model. It is important to note that using IRI focusing greatly improved the MVI model, and should always be used when inverting for the magnetization vector, as it produces a more compact distribution of vector directions. In summation, I recommend the following for the analysis of magnetic field data using MVI. I recommend to always compare both conventional susceptibility models and MVI models to better understand the solution space of a non-unique process. I also recommend to always use IRI focusing for better anomaly definition, and to focus the interpretation of magnetization vector direction on large amplitudes due to the smoothing caused by the default model norm. Lastly, I recommend that you use the ePerp and eProj scalar voxels to analyze the importance of the inducing field component and determine how to further iterate and interpret your model. Our next episode will present a few tips on preparing gravity gradiometer data for inversion, so stay tuned. For more Voxy learning material, visit the new support center at my.geosoft.com. Thanks for watching.